This is problem 1340E. It's on page 745. A 1 shell pass and 8 tube passes heat exchanger is used to heat glycerin from 75 to 140 degrees Fahrenheit by hot water, which enters the thin-walled half-inch diameter tubes at 190 degrees and leaves at 120 degrees. The total length of the tubes in the heat exchanger is 500 feet. The convection heat transfer coefficient is, and it's given there on the glycerin or the shell side, and another number is given for the water or tube side. Determine the rate of heat transfer in the heat exchanger, A, before any fouling occurs, and B, after fouling with a fouling factor that's given there occurs on the outer surfaces of the tubes. Now, first of all, let's consider this from a practical standpoint. Why would there be fouling on the outer surface of the tubes? Why wouldn't that be cleaned off? Well, in a shell and tube heat exchanger, the outer surfaces of the tube are typically difficult to access, and so cleaning the outer surfaces of a shell and tube heat exchanger may or may not really be all that practical. The inner surfaces can typically be cleaned fairly well. So typically you run the dirtier fluid, or the fluid that you expect to precipitate out more stuff through the tube so it can be cleaned out. And the cleaner fluid would make sense to run through the shell side. Anyway, let's sketch the system to begin. It can be difficult to understand what they're talking about without a picture, so let's make a picture of it. Now, there's one shell pass. Now, what does that mean? Well, that means fluid comes into the shell and leaves the shell and does not pass through a second shell. It does not pass through the shell a second time. So we'll call that capital T1. That's the terminology your book would use. It's 75 degrees Fahrenheit. That's the incoming stream of glycerin. The glycerin leaves at a temperature, let's call this T2, 140 degrees Fahrenheit, using the capital T for the shell side. On the tube side, there are 8 tube passes. What would that look like? Well, there's one tube pass, 2, 3, 4, 5, 6, 7, 8 tube passes. At least schematically, that's the idea. The tube fluid flows back and forth through the shell many times. Now, of course, it's not flowing within the shell, it's inside the tubes, but you get the idea. So your book would call this little T1. That's the temperature of the incoming stream of water. And that temperature, the temperature that the water comes in with, is 190 degrees Fahrenheit. So it's, of course, the water that's heating up the glycerin. And then the water leaves at a temperature T2 of 120 degrees Fahrenheit. Now, the heat capacity of the water was given. It's 1.0 BTUs per pound mass per degree Fahrenheit, and the convective heat transfer coefficient inside of the tubes was given as 50 BTUs per hour per square foot per degree Fahrenheit. Now, the tubes, just to note, are 1/2 inch thin walled, and the length of those tubes in total is 500 feet. So if you measured all this length together, you'd get 500 feet of tube. Now, the glycerin, as I said, comes out with a temperature of 140 degrees, has a heat capacity that was given in the book of 0.6 BTUs per pound mass per degree Fahrenheit. And if you read the problem statement, I skipped over all the numbers because it's a little bit difficult to read the numbers and make the sentence flow. So I just skipped the numbers, knowing I would come back and write them down in a schematic of the system. So the convective heat transfer coefficient on the shell side is 4 BTUs per pound mass per degree Fahrenheit. So we've got our convective heat transfer coefficient inside the tubes and a convective heat transfer coefficient outside of the tubes. Now notice that we are given all of the temperatures around the heat exchanger. This means that we could use the log mean temperature difference method, or we could use the effectiveness number of number of transfer units method. I'm going to use the log mean temperature difference method for this just to illustrate it. So let's begin by calculating the overall heat transfer coefficient, because notice we've got the two convective heat transfer coefficients And if it's thin walled, then that essentially means we're supposed to neglect the resistance of the tubing wall. So we need to find the heat transfer rate, Q dot. So there's a big given area, but the find area is just basically what is Q dot and what is Q dot when the heat exchanger is fouled. So in other words, how much does the heat transfer rate go down when fouling occurs on the exterior surfaces of these tubes? So let's find out. To begin with, I'm going to calculate the overall heat transfer coefficient. It's pretty simple. It's 1 over, and let me give some subscripts here. HO will be the convective heat transfer coefficient outside of the tubes, and HI will be inside of the tubes. So the overall heat transfer coefficient you have to add in this inverse way, as we talked about, as 1 over HI plus 1 over HO. So this is 1 over 50. I'll add in the units later. The units are consistent, plus 1/4. And so when you calculate U, the overall heat transfer coefficient, by just taking these, adding a 50th to a 4th, and then inverting it, you'll find that the overall heat transfer coefficient is 3.7037 BTUs per hour per square foot per degree Fahrenheit. So there's our overall heat transfer coefficient. Notice that the length of the tubing is given, and so the amount of heat transfer surface area, all the surface area on the exterior of these tubes, or since they're thin-walled on the interior surface, that area would be the same as simply pi dl, because basically we're thinking about taking this tube and just straightening it out. So it's just a long tube that is 500 feet long, so we just need the formula for the surface area of a cylinder. So pi d is just the perimeter, L is the length, and that gives us the surface area of that tube. So this is pretty easy. It's pi times 1/2 inch. Okay, that's the diameter of the tubes multiplied by 500 feet. Of course, we've got a units mismatch here, feet and inches. We need feet squared, so let's just multiply by 1 foot per 12 inches. The inches will go away, and our area will be in square feet. It comes out to 65.4498 square feet if you want that many decimal places. Now, to calculate the overall heat transfer rate, it would be Q equals UA delta T log mean. Now remember, forgot one thing. That's for a double pipe heat exchanger. We need a correction factor, F, and then delta T log mean. Okay, so we've got U, we've got A, we need this correction factor, F, and remember that correction factor is so that the log mean temperature difference is corrected from a double pipe heat exchanger to whatever particular heat exchanger we have. In this case, this 1 shell pass, 8 tube pass heat exchanger. Well, let's go ahead and get the log mean temperature difference, and then we'll finally get F, the correction factor for it. The log mean temperature difference is pretty straightforward. Delta T log mean is delta T1 less delta T2 over the natural logarithm of delta T1 over delta T2. Now, what are these delta T things? Well, they're just the what's called the approach temperatures. Okay, so really it's just the difference in temperature at the ends of the heat exchanger. So you want to compare, for example, the inlet temperature of the heating fluid to the exiting temperature of the cold fluid, the fluid that's being heated. So from here to here, I will call that delta T1, and from here to here, I'll call that delta T2. Now be careful, don't get confused. The fact that I've got a T1 here means nothing to this T1. Okay, these are different things. This is delta T1 that goes in the log mean temperature difference, and it's just the approach temperature on one side of this counterflow heat exchanger. Similarly, this delta T2 has nothing to do with this temperature over here. It's just a difference in temperature. So to make it clearer, let's get rid of the delta T1 and delta T2 terminology and plug in the actual temperatures we're going to use. So little T1 less T2, that's this difference over here. Now we can forget about this delta T1, that's this term, less delta T2. Well, what difference would that be? That would be T2 here less T1, so that's T2 less T1 divided by the natural logarithm of each of these terms. So T1 less T2 over T2 less T1. Now, I won't plug in all the numbers because I'm running out of space. You can do that. You see what these temperatures are. You can see little t1, little t2, capital T1, capital T2. You can plug all these things in and come up with the result. it's pretty straightforward. You should come up with a log mean temperature difference of about 47.4561 degrees Fahrenheit. That's what you should come up with. Now the last thing to find is this correction factor F. So let me, you've got all of this in your notes by now, so let me erase the U and A. And we need this correction factor. How do we find it? Well, the key is to go to the charts. There are no equations for the correction factor F. But if you go, let's see, let me find the page for you quickly. Go to page 720 in your text, and you'll see a figure that, or well, actually 4 figures that look like this, okay? So you've got all these different correction charts. You have to decide which one you're on, and we're not on the lower 2, right? Because both of those are cross-flow heat exchangers. So it must be one of these 2. Well, let's see. We have one shell pass, and looks like that would be figure A. So the figure A at the top of the page is the figure that we're interested in. Okay, that's where we're going to find our correction factor. Now, we'll have to find the parameters R and P in order to read off the correct correction factor. So let's do that next. P and R, if you look at the figure, you'll see the equations for them. P is T2 less T1 divided by T1 less T1, where I'm using upper and lower case temperatures here. Let's just go ahead and plug in the numbers. I've got enough space to do it this time, so I'll do it for these. T2 is 120. That's the temperature of the heating stream out. T1 is the temperature of the heating stream in. We have to divide that by capital T1, which is 75, less lowercase t1, which is 190. Now P comes out to about 0.61. And then R is capital T1 less capital T2 divided by lowercase t2 less lowercase t1. So what is this? Well, this is just the change in the temperature of the cold fluid divided by the change in temperature of the hot fluid. So 75 less, let's see, 140 divided by 120 less 190. Plug that into your calculator, you should find that this is about 0.93. Now both of these are non-dimensional. We're supposed to use these two numbers to find the correction factor F on chart A. Now what you'll probably notice is that this is off of the chart. 0.61 for the x-axis for P is pretty straightforward. Let me hold up the book so you can see this. So 0.61 on the x-axis, that's pretty easy to find. Okay, 0.6 is right here, 0.61 is to the right of it just a bit. So that's no problem. The difficulty comes in finding R. R is 0.93. Now there's a curve for 1 and a curve for 0.8. Notice R tells us what curve we're on. There's a curve for 1 and a curve for 0.8. But the problem is that curve gives out essentially before the 0.61. So basically what we have to do is, I would say, visually extrapolate this chart. Obviously this is not going to be terribly accurate, so it might be better to go with the effectiveness number of transfer units method. Anyway, my best guess basically from this is that the correction factor F is very roughly 0.45. That's my best estimate. Would you be wrong to say it's 0.4? No, that'd be fine. We're not even really on the chart, and so it's very difficult to estimate a good value for F. But now we have all of the pieces that go into the puzzle. And so now I will go ahead and plug them in. The overall heat transfer coefficient, 3.7037 BTUs per hour per square foot per degree Fahrenheit. The area was 65.4498 square feet. I'm off the video if I keep going to the right, so what I'll have to do is go below and continue multiplying. Now the correction factor F we just found is 0.45 or so. And then the log mean temperature difference was 47.4561 degrees Fahrenheit. So the degrees Fahrenheit go away, the square feet go away. We'll have BTUs per hour. So the number of BTUs per hour is about 5,177 BTUs per hour. So there's our heat transfer rate. Now, what's going to change with fouling? So by the way, that's the answer there. What's going to change with fouling? Well, with fouling, there's just going to be more resistance to heat transfer. Now, the fouling was given in the problem statement. I did not write it down, but it was given. And all it does is it adds to the resistance. So basically, instead of just having 1 over HI plus 1 over HO, we're going to have some fouling resistance to add into this overall heat transfer coefficient. So again, this is 1 over 50. Let's be careful of the units BTUs per hour per square foot per degree Fahrenheit, plus 0.002 that was given in the problem statement, hours square feet degree Fahrenheit per BTU, plus 1 over 4 BTUs per hour per square foot per degree Fahrenheit. So now we have to add all this mess together. When you do that, you find that the overall heat transfer coefficient U is 3.6764 BTUs per hour per square foot per degree Fahrenheit. Okay, so notice that the overall conductance, if you will, or the overall heat transfer coefficient, has gone down a little bit. It was 3.7 something, now it's 3.67 or so. So when you plug that in, okay, plug in the new overall heat transfer coefficient, then what you find is that the heat transfer rate when there's fouling is a little bit lower, 5,139 BTUs per hour. Now, if you were designing this heat exchanger or specifying it, what would you do? Well, what you should do is realize that eventually the heat exchanger is going to be fouled, and if the heat transfer rate here is not large enough when it's fouled, you need more surface area. So, you basically need a bigger heat exchanger. If this is acceptable though, then you're done and it works.